Hello, in this video we're going to look at the exponential family and specifically the Poisson distribution within the exponential family. And this is a follow-up video from a video that I called the exponential family mean and variance, where we generically found the mean and variance for any exponential family. And in this video we're going to show that that technique works for any specific distribution and is often easier than finding it in the traditional methods. We showed that these two forms are exponential families. So if you can sort of trick or manipulate the distribution into one of these forms, then it is considered the exponential family. So I'd recommend going back and watching that video. For this one here, we're going to look at the Poisson distribution, and it's of this form where the parameter is positive and x, it takes on 0, 1, 2, and etc. Now we need to start manipulating this to look like an exponential distribution. So what we do is we take the e and the log of it and we get this. Now within the log we can start manipulating, and perhaps I probably should have left the exponential out, but we'll get to that. So then we take, then the log of a division is the difference, so this comes out as a minus, and then that's the log of multiplication that becomes addition. So, and then when you do that, the exponent can be taken out front, and so this e, well, yeah, the log of e of minus lambda is just minus lambda. And then here we get minus log of x factorial. But since this doesn't really play a part, we can take the e to the log and actually bring it back out. And I wish I would have just left it out to begin with. But this was my thought process initially. And that's why I'm like, well, if you do this, then you may do the same thing, but then realize that there's no parameter in this. It's only data. It's not a parameter times data, and so really it should have been left out, and that's why I take it out here. And then here we just leave it the same. So this is the exponential form, where this is your h of x, this is your eta of lambda right here, this is your sufficient statistic, and this is your log partition. And notice it's, the form is minus a of theta, so this right here is just, the log partition is just lambda. Now to put it in canonical form, we do this. We write an eta of x instead of log of x. We just call that eta. And then we have to manipulate this log partition into something that gets us the minus lambda back. And that's e to the eta, right? Because if you put in log of lambda here, then you just get eta back. And so this is the canonical form, and this is the form that we'll use to find the moments of our sufficient statistic. So here we have the mean, and the theory tells us that the mean of the sufficient statistic, in this case it's x, is just the derivative of the log partition with respect to eta, which the log partition was e to the eta, which is this, and the derivative is just e to the eta. Now if we stick in what we know about eta, which was log of lambda, those cancel and we just get lambda, which we know is the mean of a Poisson distribution. Now the variance is the variance of the sufficient statistic, and that's just variance of x. That's the second derivative of our log partition, which is this. And you take derivatives twice, you just get it back. Now stick in the value of what we know eta is, which is log of lambda. The e and the log cancel and we're left with lambda, which we know is the variance of a Poisson distribution. Yep. Well, that's all I have for today. Hopefully you enjoyed it. I sure did. Like the video and subscribe so you don't miss the next one. Thanks. Bye.